Hi, physics students. So we are working on warm up 2-3, warm up 5-3, which covers a review for our quiz today. So our quiz is focused on LOL charts, and in these LOL charts, you are defining the system yourself. So you have a bit more control over your answer than you would in the concept builder that you did, where they gave you LOL charts and they defined the system for you. So in this scenario, we've got a rubber band that's stretched across your finger and launched across the room. There are many different ways to answer this question, and they all could potentially be correct. It also depends on your interpretation. So I'm going to cover all the different scenarios that students mentioned in class. So the rubber band being stretched across your finger, right off the bat, a rubber band stretched has elastic potential energy. And then the rubber band flying across the room, if it doesn't say that there's a height change, I'm not going to include gravitational, and that's going to transfer the elastic potential energy to kinetic energy. Now, some students wanted to add a gravitational energy because it's above the ground. And so if you included gravitational potential energy and it doesn't mention a height change, you want to make sure that it's equal on both sides. Now, I had some students, before you complete this, you want to make sure to identify the system. So rubber band, Earth, you always want to include Earth if you want any gravitational potential energy, and I just do it as a default right off the bat. So, and then you can include the person. Now, I didn't include the person in this energy chart because the person isn't adding any energy to the energy of the rubber band as it flies across the ground. But some students thought that the person needed chemical energy to get the rubber band stretched and hold it stretched. So that's a valid reason to have chemical energy. If the person is part of the system, you can add chemical and include that chemical energy here. And then once it's released, you can say that the person has exerted that chemical energy, and you can add it to kinetic energy to balance things out. I don't necessarily think that the person is contributing to the kinetic energy of the rubber band. So again, if you don't want to include chemical and leave it as this, that's perfectly fine. And because there's no height change, if you don't want to include gravity, you could leave it as this. Many different possibilities for this answer. And again, the number of blocks used doesn't matter either, as long as they're equal on both sides. For the next scenario, we've got a gymnast that jumps on a springboard and does a flip in the air. So the gymnast is at the lowest point of their bounce on the springboard. Springboard is a key word to know that there is elastic potential energy. If they are at their lowest point, you don't need gravitational potential energy. If you want to include it, you want to make sure you increase it in your final state. Here I'm going to leave it as no gravitational potential energy. And if this person is at their lowest point of the bounce, they're at a moment of rest where they are changing direction. So I would say no kinetic energy either. Again, let's define the system. The gymnast, the earth, the springboard. Okay. In the final system, we've got the gymnast flipping in the air. They've got kinetic energy and they've got gravitational energy. There's motion and they're higher above the ground. So I have an imbalance here. I've got kinetic and gravitational to add to 2. If I want to balance it out, I could include 2 elastic potential energy. Now, I had some students say, would we have thermal if the student is bouncing and colliding? Well, in my mind, if you had thermal, the collision happens before the person is at the lowest point of their bounce. So I would say that the thermal energy was there, but at the point of this initial position, it's no longer a part of energy in the system. If you did include thermal, your collision aspect would work, and I would give you points for that as well. But in general, thermal energy was part of the collision, but at the lowest point, the collision is already passed and done with, so I wouldn't include it. Now, another thing that students included was chemical energy from the gymnast. And that makes sense. If the gymnast is pushing off of the springboard, they are exerting energy, and that energy is contributing to maybe more motion or contributing to more height. So if you do want to include chemical energy, that would be fine as well. It's all on how you interpret it. If the person is just flatly bouncing and all the elastic energy is what gets her height and motion, then you can exclude the chemical. But either way, both of those explanations are valid in understanding energy flow. One thing I want to mention is if you decide not to include the gymnast as part of the system, but you think that the gymnast does contribute energy, you can also show this as energy coming in from an outside source, which would be the gymnast. So this is another way that you can show correct energy transfer for these LOL charts. There might be more, so if you have any others that you want to talk about, feel free to reach out to me. So the next thing we're going to do is part 2 of the Energy Spring Lab. So in this lab, I actually changed it for the class. Instead of finding the force of each compression, we're going to find the spring constant, and I'm going to walk you through that process. We did not end up doing the elastic potential energy, so this we're going to do next class. And also, I'm going to take all the spring constants that we got for this period, and we're going to take the class average to make sure that that our data is as close to accurate as possible. The compression distance we're going to collect for settings 1, 2, and 3, and I'll walk you through that process. And then at the very end of this, when you're done, you're going to draw an LOL chart for the data that we collected in the scenario of compressing and uncompressing the spring in a spring cart. Okay, so in this simulation, I'm going to just demonstrate how we collected our force distance data to get our spring constant. This part right here has a force sensor using this kind of plunger at the end. And this right here is our spring. The spring compresses into the 3 different positions that you can see here. There are 3 different positions. It compresses to position 1, position 2, and position 3. We are going to calculate the actual distance that each of those compressions are. But what I want to show you is how the force increases as we compress it over a certain distance. We're going to graph that and find the spring constant from it. So all we're doing is we are compressing the spring onto this force sensor and making sure it doesn't move back and collecting the data. So I'm going to go really slow and just continue to slowly compress my spring until it stops. So this is a recording of that data. I'm going to scale to fit and highlight the line that I have here. By highlighting this line, I'm able to get a linear fit for just this semi-linear data. Obviously, there's some sources of error because every time I reach a position in my
my spring, it stops me for a second and adds a little resistance. But if I were to take a good amount of these points on the line, that should reduce the sources of air that I have here. So I get a spring constant of 187, and that's going to go into your table.
So when we are measuring our distance, you guys are going to do it using my Pasco Capstone data collector because we can measure distance. My students did it with a ruler in class, but all I'm doing, and you're going to see the video here, is pushing my cart from this 0 position and then stopping at position 1. And then for position 2, I started over again from 0 position over to position 2. And whenever it stops on the graph, you'll see the distance that it has traveled. So I'm going to do that for all 3 positions.
Here's position 1. .0112 meters. Compression 2. My distance here, once it settles, is 0.0281 meters. I'm going to try position 3 again. .0455 meters. All right, so I'm just giving you this as a summary of the information we collected. We got a spring constant of 187 newtons per meter. You don't need to do anything else for that. We got a compression distance for position 1, position 2, and position 3. You're not going to use this to calculate elastic potential energy. Again, we're going to do that next class after I've gotten an average of everyone's values, as well as the spring constant. I'm going to get the average from the class, and we're going to use that average to get our elastic potential energy to reduce the amount of error that we get when we analyze our information. Now, for the LOL chart, you're going to pause the video, complete this yourself, and then continue the video when you're ready to check your answer. So for this last question, I want you to try it out before I demonstrate it. We are doing an LOL chart to analyze the spring when it is uncompressed, when it is compressed, so person, compress to position number 1, and then person compresses it to position number 2. So each position you are compressing your spring a little bit more, it gets a little bit tougher to compress it as the stretch gets bigger, as the compression gets bigger and bigger and bigger. So initially it's hard to figure out where the uncompressed part of this system is coming from, where the energy of an uncompressed spring is coming from, until you read scenario number 2. There is a person that compresses the spring. That person is the potential energy when we start. So before we start, we're going to add all the objects that are in the system. The spring cart, the earth, the person, and there's an R there, and the ramp. So the scenario says that the spring is uncompressed. It doesn't mention the person,
But it does state in the next part that the person is what compresses the spring. This is where the energy is stored in the person in terms of chemical energy. I'm going to give it 4 squares. It doesn't matter how many squares you give it as long as it's equal. So I start with stored energy in the person. Nothing is happening yet, but that energy from the person is going to transfer to the compression of the spring. When you compress the spring to position 1, you're going to have some elastic potential energy. So I'm going to have maybe, since it's position 1 block of elastic potential energy. So if I take 1 block and move it to elastic, I'm going to have 3 blocks left over. This is still chemical. I'm going to use the same system. Spring cart, person, ramp, earth. You want to keep it consistent. Next, I'm compressing it to position 2. So my elastic potential energy gets even larger. I'm going to take 1 chemical energy, because that's where the elastic energy is coming from, to push it. So this is more elastic, and it reduces the chemical. We want to keep it consistent. If I start with 4 here, I need to make sure I have 4 here, and I have 4 there. So that would be your energy transfer in this scenario.